What is niacinamide? Niacinamide is an amide of vitamin B3. It can be seen from the structure of vitamin B3 and niacinamide, where at vitamin B3, the compound being attached to the carbonyl group is OH. Meanwhile, at niacinamide, the OH is substituted with NH2 that indicate amide. Hence, it's called as amide of vitamin B3. Some of the characteristics of niacinamide are: first, photoprotective, where the skin able to cope with molecular damage caused by sunlight. Second, it has lightening effects that help to brighten the skin. And third, it is microbial, which is it able to fight microorganisms, hence it can help to prevent acne. Due to these characteristics, niacinamide is a safe compound often used in cosmetics. The industrial process for production of niacinamide is referred to the Lonza Group Pharma and Biotech in the patent US 5719045. Reaction in the production of niacinamide can be divided into 5 steps. First, 2-methylpentanediamine to 3-methylpiperidine, 3-methylpiperidine to 3-picoline, side reactions of picoline, picoline to 3-cyanopyridine, and lastly 3-cyanopyridine to niacinamide. The process begins with 2-methylpentanediamine as the starting raw material, which will first be vaporized and then converted to 3-methylpiperidine through exothermic reaction with the presence of zeolite catalyst. The 3-methylpiperidine is then dehydrogenated endothermically to 3-picoline over a palladium catalyst. The 3-picoline then will be divided into 2, which is 90% and 10%. For the 10%, the side reaction will convert picoline into various byproducts, including nitrogen gas, carbon dioxide, and water. Meanwhile, the remaining 90% of the picoline undergoes an exothermic emulsionation with the presence of vanadium pentoxide catalyst to form 3-cyanopyridine. And finally, 3-cyanopyridine is converted into niacinamide via an enzymatic hydrolysis process under condition of pH more than 7. The process for production of niacinamide is divided into 3 blocks. Block 100, reaction train in which MPDA is converted to PIC. Block 200, reaction train in which PIC is converted to niacinamide. And Block 300, purification and separation of the niacinamide to obtain necessary purity. However, the summary on the explanation of the reaction will only be explained for Block 100. Okay, so before I start the explanation, I want to clarify that the value of the flow rate I obtained from this table that is included along in the journal. Okay, so the reaction will start from the storage tank T101 that stored MPDA, which is the starting raw material. The initial flow rate is 3306.93. Okay, so from the S101, the first stream, it will go through pump, and then it will here at M101, which is mixer. The stream from S109 and S102 will be mixed here. So that's why we can see the changes in the flow rate, where the amount of flow rate for MPDA is increasing, and there is another substance included in the flow rate, which is ammonia and methylpiperidine. The existence of new substance in the flow rate, which is ammonia and methylpiperidine, actually it comes from the stream S109. Okay, so here we can see for the value that being highlighted, actually it is in the unit of E notation. Unit E notation actually is a unit that indicate for the number that are too small to be conveniently written in decimal form. Hence, it is not included in the total flow rate, which is because the number is very small, so we not include along in the total flow rate. Okay, then the flow will go through heat exchanger and then to the compressor C101, and then here at the compressor it will increase the pressure of stream S104 for it to enter the first reactor. So at the first reactor it will convert MPDA to MPI. As we can see, at the stream that exit the first reactor, the value of flow rate for ammonia and MPI increasing, meanwhile the flow rate for MPDA is decreasing. This is because at the first reactor, it convert MPDA to MPI and give byproduct, which is the ammonia. Hence, it explains why the flow rate of ammonia and MPI increasing while the flow rate of MPDA is decreasing. Okay, so the existing stream from the reactor will enter distillation column. Okay, at distillation column, the stream will be divided into two, which is at stream S10A, which is the separated MPDA, and stream S107 for ammonia and MPI. Okay, I will explain first for the stream S10A. Okay, the distillation column, its function is to separate MPDA from the previous stream to be recycled. So from S10A, it will flow through the pumps to being increase the pressure to enter the mixer again. Okay, for stream S107, it will pass through the compressor, which is to increase the pressure, and it will enter the heat exchanger, and then it will continue to enter the second reactor. Okay, the function of the second reactor, it will convert MPI to PCI. So that's why we can see at the existing stream from the second reactor, which is the S112, there is the presence of H2 flow rate, hydrogen flow rate, because the conversion of MPI to PIC will give byproduct hydrogen gas. And also the flow rate of MPI is decreasing due to the conversion, and there is the new presence of PIC. Okay, the flow rate of PIC. Next, the stream S112 will enter the absorber that will separate hydrogen and also ammonia from the stream. That's why we can see it will be divided into S113 and S119. And we can see at the stream S119, the flow rate that visible is only MPI and also PIC. Okay, because hydrogen and ammonia is already been separated and go through stream S113. Okay, so here this stream will be used as a material for block 200. Meanwhile, for the flow rate of S113, it will continue to pass through this absorber, the second absorber, and we can see at S115, which is the resulted stream from the absorber, it shows that the flow rate of ammonia is decreasing. This is because the ammonia is being absorbed in the absorber, so it only left with hydrogen flow rate. So the hydrogen that being left at the stream S115 will be used to Dalton heating system. And lastly, at the stream S11A, the remaining ammonia and water stream will be fed into the splitter for the process at the second block. For the real-life application of niacinamide, it is widely used as an ingredient in skin cosmetics, which is skincare, due to its benefits such as whitening agents, antioxidant, and moisturizing effect. So here is a few examples for cosmetic brands that use niacinamide in their cosmetic formulations. The safety issue may occur due to the varying changes in federal regulations. For example, if the regulations of water and air quality is increasing, the manufacturers will try to save costs by reducing the usage of water in cleaning streams. Hence, it will lead to safety issues such as leakage of harsh and carcinogenic chemicals formed as intermediates in the pathways to the production of niacinamide. However, this production method with patent US 5719045 is promoting green chemistry. Hence, the increase in regulations will not give any bad safety issue, as the process requires very little toxic intermediates and relatively simple exhaust gas and wastewater cleanup.